Okay, the purpose of this video is going to be to find three separate derivatives using the limit definition process. I've reminded you of the formula for the definition of derivative in red. And just remember, this is the slope of a secant line between two generic points on any graph f. And this limit is how that secant line turns into a tangent line. We let the space between those 2 points get infinitely small, so those points get closer and closer together, and the result is the slope of the tangent line. So this derivative found with the limit process, these three examples are a little bit tougher than the ones we've done in previous videos. And so I would encourage you to pause right now and try to answer this blue question. Just find the derivative of this blue function, and to do that for each of the three examples. So if the function's called f, we're going to call the derivative f prime, and it's going to be a limit as delta x goes to 0 of the function evaluated at x plus delta x. That's just replacing x with x plus delta x in the function. So there it is. The function's just a simple square root. My x turned into x plus delta x. The next thing is just the function. So there's part 1 and there's part 2, minus sign in the middle, and then delta x in the bottom. Okay, so far I haven't done any real hard work. I've just literally substituted into the formula. Okay, so my next step is going to be to simplify. And as is the case with all of these problems, you can't just sub in 0 and take the limit, because the bottom of the fraction, the denominator, is delta x. So if you were to sub in, you would have 0 in the denominator. And we've seen a couple of different ways to start canceling things out. If it's a polynomial, usually you just square out things, combine like terms, and factor out and cancel. If it's a fraction, you might have to do a common denominator. In a square root, if you remember from some of our limit taking discussions, a lot of the times when you need to simplify a limit that involves a square root like this, you want to use the conjugate. We want to multiply the top and the bottom by the square root of x plus delta x plus 1 plus the square root of x plus 1. Multiplying by conjugates makes a lot of good things happen. Basically what happens every time is, if you think of this as FOILing, it makes the O and the I, the inner and the outer parts of FOIL, disappear because they're conjugates. And what's left over is going to be something that's much simpler. So when I take this first square root and multiply it by itself, I get the same expression with no square root. So I get x plus delta x plus 1. Then I do plus my one square root times my other, and then I turn right back around and do minus one square root times the other. That's why those two things go away. All right, that's why you use the conjugate, because the middle two terms cancel each other out. Then I get the last square root times itself, and that's subtracted, so I have minus x plus 1 on top. So the top already looks much simpler, doesn't have any square roots left, which is a good thing. Now the bottom, I've got delta x times this big set of parentheses. Let's just leave it. Let's not bother trying to distribute anything. There's not much we could do with it anyway. But I'm just going to multiply delta x by this set of parentheses and leave it the way it is. When we sub in just a minute, we'll see that we're much better off just leaving that the way it is. Alright, so now we're in kind of a familiar spot. We've got some things canceling. Look on top. X here minus x here, because this negative sign is going to apply to both parts of the parentheses. I also have a plus 1 and a minus 1, which leaves me with nothing on the top but delta x. And because we didn't try to somehow combine on the bottom, look what's left on the bottom, delta x. So I can go ahead and get rid of that too. You can never cancel out something that is added to something else, but once I cancel the other 4 things on top, that delta x was the only thing up there, so I was free to cancel it with that delta x on the bottom, leaving me with just a 1 on top. So the only thing I'm left to take the limit of is 1 on top. And these parentheses, I don't guess I need the parentheses anymore. They're not going to hurt. These two square root symbols on the bottom. Now I'm going to take the limit. Now at this point when I plug in delta x equals 0, I'm not getting an undefined expression with delta x only on the bottom. This delta x shrinks away to nothing. When we take the limit at 0, that's what happens. Delta x becomes 0. And see what's left. I've got a 1 on top. I've got a square root of x plus 1 here. And I've got a square root of x plus 1 here for a total of 2 square roots of x plus 1. This is the derivative of this. F prime of x is down here. Okay? So there's one good one. If you've got a square root, a lot of times you're going to use that conjugate process to simplify enough to where you can plug in. All right, here's our next example. The function we're dealing with is 1 over x squared. We're going to do the same process. Please pause here, try this process, and then come back for the answer. Okay, so we're going to substitute in. I've already included the definition of derivative. F of x plus delta x. Let's see, our function's 1 over x squared, so evaluated at x plus delta x, I'm just changing this x to x plus delta x. Minus the function, it's just minus 1 over x squared, all over that delta x on the bottom. Okay, so this is the type where I've got fractions, and almost every time when you have fractions similar to these, it's going to be a situation where you want to get a common denominator and add the two fractions, or in this case subtract. I need to multiply this first fraction by x squared, top and bottom, in order to get the common denominator of x squared times x plus delta x quantity squared. I need to multiply the second fraction by x plus delta x quantity squared. Okay, so you can see how this multiplication is going to give me a common denominator. So now what I have on top is x squared minus x plus delta x squared. And what I have on the bottom is my common denominator, x squared times x plus delta x squared. And don't forget, all of that's the numerator and delta x is the denominator. So I've got a kind of fraction within a fraction here, and that's sometimes kind of awkward, but just be tedious, keep all of your steps, and you should be fine. So what I want to do next is to square out the top of the top. This binomial squared right here, I'm going to square it out. I'm not just going to square both parts. I'm going to FOIL it out. I'm going to write it twice and square it all out. And the result of that is x squared plus 2x delta x plus delta x squared. Okay, I didn't write it twice and show that, but that's this thing multiplied by itself. Okay, then the denominator of the top fraction, still x squared times x plus delta x squared. And then the denominator of the whole thing is delta x. Okay, so moving up here, let's keep going. Still taking the limit. The last thing I'm going to do. And look what happened in this one. X squared, negative x squared, because that negative applies to all of it. And what's left in the numerator of the numerator, everything there has a delta x in it. So let's factor that delta x out. We did this when we worked with some of the simpler ones with the polynomials. I'm left with 2x. Actually, I'm left with negative 2x because this negative sign applies to everything. So I've got negative 2x minus delta x over x squared, x plus delta x squared over delta x. Okay? Now, I want to start canceling things by doing this. Instead of dividing by delta x, let's multiply by 1 over delta x. And that just makes it more clear that this delta x and this delta x cancel out. Sometimes with a fraction within a fraction, you're not sure whether those two delta x's are going to combine to be a squared delta x, or whether one's going to cancel the other one out. So rather than writing it as divided by delta x, I'm going to write by multiply by 1 over delta x, and that makes it look a little clearer. Now I'm in a situation where I can sub in delta x. What happens if delta x approaches 0? Well, this term goes away, this term goes away, and on top I have negative 2x, and on the bottom I have an x squared here and an x squared here for a total of x to the 4th. Cancel 1x from the top, 1x from the bottom, negative 2 over x cubed. All right, the derivative of 1 over x squared is negative 2 over x cubed. All right, so there's number 2. All right, last example for this video. Again, pause and try it. There's going to be quite a bit of multiplying things out in this case. I might have to pause and catch up myself for the sake of time, but let's see how it goes. All right, so first thing is f of x plus delta x. So this function has 2 x's in it, an x cubed and just an x. So this one's going to be quite a bit more complex. So it's going to start with x plus delta x cubed plus x plus delta x. That is right there, f of x plus delta x is this, all right, the whole thing, minus x cubed plus x all over delta x. So I'm back to a polynomial. I don't have any square roots, I don't have any fractions, I've just got a lot of multiplying out to do. So see this x plus delta x cubed, that's going to be the majority of it. I'm going to pause, multiply that out, and then be right back. All right, so I'm back after some multiplying. I've shown how you cube the x plus delta x. That's cubed out up here. If you remember how your binomial formula, you can cube that quickly, but otherwise it just takes a little bit of time. So all of that turned into this. Then I also had the x plus delta x here, which went here. And then I also had the minus x cubed plus x, so I went ahead and distributed the negative sign here. So all said and done, I've got all these terms that need to be simplified. And it's kind of like some of our earlier, easier examples. Anything without a delta x in it should go away. X cubed minus x cubed plus x minus x. Everything else has at least one delta x in it. That's what I want to factor out and cancel. Limit as delta x goes to 0. Let's get that delta x out and see what's left in each term. 3x squared plus 3x delta x. See, this term had 2 of them. It had delta x squared, so when I took 1 out, I was left with 1 in. Delta x cubed, I take 1 out, I'm left with 2. And then the term delta x, when I take delta x out, I'm left with plus 1. So when everything that's left has a delta x in it, some of those terms will still have delta x in it, some of them will not. But the good part is, the reason this happens the way it does, is that delta x and that delta x can cancel. Now I can take the limit. When I take the limit and let delta x approach 0, this term, gone, because delta x is in it. This term, gone. It has a delta x in it. My final answer is 3x squared plus 1. Okay, so the derivative of x cubed plus x is 3x squared plus 1. And while we're just working on these examples, take a minute to remember, do you know what a derivative does? What does f prime of x even mean? It's a function that will give us the slope of f at any x we decide. All right, so there's 3 good examples, a little bit more involved than our previous ones, but you really need to know how to do these by the limit definition.